Okay, let's dive into this material you sent over. It's all focused on fractions, sort of the ground floor. Our goal here really is just to unpack what your sources say they are, how they work, how they're, classified.
Absolutely. And, well, the sources start right where you'd expect, that classic idea.
Yeah.
Take a whole, maybe an apple,
Right, the apple analogy.
and slice it up into equal bits. That's the core visual they use.
Makes sense. So 5 equal slices, one slice is 15. Grab 2, you've got 25. It's really about showing a part of something whole.
Exactly. And your material gives us the formal notation too, abe, where A, the number on top.
That's the numerator, counts the pieces you have.
Right. And B, underneath, that's the denominator.
Mm.
Tells you how many equal pieces the whole thing was split into. Kind of like the name of the fraction size.
Fifth parts or third parts or whatever it is.
Precisely. And a really crucial point your sources hammer home right away, B, the denominator. It just cannot be 0.
Division by 0, undefined territory.
Not defined in this context. So starting there, your sources then branch out, classifying fractions. What were the main types they pulled out?
Well, the first big split seems to be proper versus improper.
Yeah. Proper is numerator smaller than the denominator, like 45, less than 1 whole.
Okay, so improper must be the reverse. Top number bigger than the bottom.
We're equal, yeah. Like 75 or maybe 55 even. That represents 1 whole unit or, more than 1.
And that connects to mixed fractions, right? The ones like, say, 2 and 57.
Exactly, yeah. Your sources show how you convert between those improper ones and mixed numbers, basically just pulling out the full units hiding inside the improper fraction.
So 75 becomes 1 and 25, same value, different look.
That's it. Just different ways to write the same quantity. Your sources also mention another classification, less about size, more about the kind of numbers involved, simple versus complex.
Okay. What's the difference there, according to your material?
Well, a simple fraction, the way they define it, just has regular whole numbers, integers, top and bottom, like 38.
Straightforward enough, so complex is not that.
Pretty much. That's when the numerator or the denominator, or maybe both, aren't just simple integers. The sources give examples like 1.4 over 8.
Oh, like a decimal inside the fraction?
Yeah, or even a fraction divided by another fraction, like 914 over 2 and 37, that kind of thing.
Okay, got it. So it's more about the structure. And you mentioned that 0 denominator thing again. Your sources connect that back to this classification too.
They do. They make a point of saying that things like 80, because they're undefined, they don't get classified as simple or complex. They're sort of outside the system.
Right. Doesn't sit in either box because it's fundamentally not a defined number in this way.
Exactly.
So we've got what they are, the different types, but they're not just labels, right? Your sources talk about using them, operations.
Oh, yeah. Addition, subtraction, multiplication, division, the usual suspects. A key thing from your material, especially for adding or subtracting, is dealing with different denominators.
Unlike fractions, yeah.
Right. Your sources really stress that you need to find a common denominator first. Get them into the same size pieces before you combine.
Makes intuitive sense. You can't easily add fifths and thirds directly. You need to convert them to, say, 15ths first.
Precisely. Convert them into, like, fractions. And there was another neat little operational rule your sources pointed out, using the word of.
Oh, right. I saw that of means multiply.
That's what they state, yeah. It's a useful shortcut. When you see of between fractions or numbers, like their example, 13 of 18 kilograms.
It just means 13 times 18 kilograms.
Exactly. Which gives you 6 kilograms. Super practical.
Definitely. And what if you have a whole string of operations? Like adding, multiplying, maybe brackets?
Well, your sources confirm the standard order of operations. They mention the Bauduin-Mayes rule.
Brackets? Of, division, multiplication, addition, subtraction.
That's the one. Follow that order, and you get the right answer consistently.
So it feels like your sources really build it up logically. Start with the apple, define the terms, classify the types, then give the rules for putting them together.
They lay out a solid foundation. And, after covering those basics, they introduce something, well, a bit surprising, almost counterintuitive, about how fractions relate to each other.
Oh,
Yeah.
like what? What's the surprising part?
Well, there's this method they present for finding a new fraction that sits right between any two fractions you pick. Let's say you have AB and CD.
Okay. How do they say you find one in between?
It's remarkably simple. You just add the numerators together, so A plus C, and then you add the denominators together, B plus D. The new fraction you get, A plus C, B plus D, that fraction will always be between the original AB and CD.
Wait, hang on. Just add the tops and add the bottoms
Right.
separately. That sounds way too easy. Does that actually work consistently?
It really does. Your sources show this method. It's kind of neat, isn't it? Shows that even simple operations can reveal these slightly unexpected relationships between numbers.
That is interesting. So, for you listening, think about what this means. We've seen how your sources break fractions down from apples to ab, proper, improper, complex, and the rules like BODS and of, meaning multiply. These are the building blocks.
Mm-hmm.
But then you get these little insights, like that simple add the tops, add the bottoms trick for finding a fraction in between. Understanding these fundamentals and these relationships from your material really sets you up.
And just think about that in-between rule for a second.
Yeah.
If you can always create a new fraction between any two existing fractions using that simple addition,
Right.
what does that tell you about the space between any two fractions on the number line? How many fractions could you potentially fit in there?
Huh. If you can always find one more, it suggests there could be an infinite number of fractions between any two.
Precisely. Kind of mind-bending when you think about it, starting from just slicing an apple.